Thank you for coming to my presentation. The title is Continuous Optimization for Distributed Big Data Analysis. In this talk, I am going to focus on the design and concept of how to achieve the high-performance big data analysis platform based on our experience. Treasure Data is a company providing a data analysis platform on cloud services. So based on our experience, I'm going to provide some tips and designs to provide the reliant and high-performance big data analysis platform. So at the beginning, I'm going to let me introduce myself. So my name is Kai Sasaki. I'm a software engineer working at Treasure Data. And as I said previously, Treasure Data is a company who is providing the big data analysis platform on cloud. And we are using Hadoop and Presto as a distributed SQL engine. So I belong to the team who maintain these distributed analysis platforms. And I'm working in Treasure Data for about 3 years. But before that, I was working at the Yahoo in Japan. And in there, I also developing a big data platform using Hadoop and Presto and Spark. So most of my career is focusing on creating a high-performance big data analysis platform. So I'm going to talk about that mainly. And also, I'm a committer of Apache HiveMore. Apache HiveMore is a scalable machine learning library running on Hive and Hadoop. HiveMore itself is just a collection of UDFs which can run machine learning algorithms as a Hive UDF or Spark UDF. In the 1 or 2 years ago, HiveMore joined the Apache Incubator project. So now the development is actively done, and I'm working as one of the committer of Apache HiveMore. And based on my experience on big data infrastructure, I wrote several books about Apache Spark and Apache Hadoop. They are the little old books, but most of the contents of this book can be applied to the up-to-date technologies and your daily work. And also in this fall, I published another book about deep learning in the browser. This book describes about the TensorFlow.js, which is a pretty new library published by Google recently. I'm not an expert of machine learning and deep learning, but thanks to my intensive contribution to TensorFlow.js, some committers of TensorFlow team invited us to write a book. So that's myself. So as I said before, in this talk, the main topic of this talk is design and the concept of how to achieve high-performance big data infrastructure on the cloud services or cloud technologies. So I'm not going to deep dive into the technical details or usage of softwares, but I'm going to provide high-level overview of these designs and concept and architecture. So I hope these designs and tips and good practices will be useful for even your use cases. So the main takeaway will be these designs and notion you can take in your daily work. So this is the topic of this presentation. First, I want to describe what is Treasure Data, who we are, and what we are doing. And in the Treasure Data, we are providing big data processing analysis platform. So we are going to define what is distributed data analysis and what is the problems of that. platform. And I'm going to describe the challenges we have based on our experience. And finally, I'm going to introduce our approach to solve these challenges. So first, we are Treasure Data. Treasure Data is a company which is providing the data analysis platform based on cloud services like AWS or Azure services. Our user can collect data from their client services like mobile devices, laptop, and wearable or IoT devices. And the data collected by these devices is safely stored in our storage system called on the cloud services. And on that storage, you can use our Presto or Hadoop cluster to do some analysis, joining the third-party data, like third-party cookie or other services behavior logs. And this data also can be exported to the other BI tools or other digital marketing tools. So Treasure Data, by using Treasure Data, you can do end-to-end data analysis for your business. And Treasure Data is founded in the 2011, and the main headquarters is located in Mountain View, California. So we are basically the Silicon Valley company, but I'm working in the Tokyo office. And the services we are providing is DMP and CDP. CDP is a customer data platform which analyzes the customer behavior and demographic information. And recently, IoT data is collecting. And fortunately, in this fall, ARM Holdings acquired us. ARM is, as you may know, the company which is creating the semiconductor chip design. So we are now a part of the semiconductor company. And now ARM is creating a new IoT platform, data from their chips. So Treasure Data is a part of their IoT platform now. And also, we are publishing several open source softwares. The most famous one is Fluentd. Fluentd is now a project of the CNCF, Cloud Native Computing Foundation. And there are many users all around the world. Fluentd is a unified data collector. By using several kind of plugins, you can collect any kind of data from your storage and other storages. Embark is a bulk loader. Fluentd is a streaming type log collector, but Embark can do the same thing in a batch manner. This is also the pluggable architecture, so you can create any kind of plugin to import the various kind of storage system. DigDag is a workflow. And as I said previously, HiveMore is a machine learning library. And in addition to these 4 open source softwares, we are publishing various kind of open source software. So please check the Treasure Data site if you are interested in the open source softwares we are creating. This is the scale of our platform. So in every second, we import 1 million records in our storage system, and 30 trillion records is processed per day by our query engine system like Hadoop and Presto. And also, in order to secure our storage system and get the trust from our customer, we get the ISO authorization. And so Treasure Data is basically the enterprise-ready data analysis platform. And as I said before, ARM is now part of the, Treasure Data is now part of the ARM. And ARM is providing the new IoT platform called Perion, which is a device-to-device platform. This platform do the device management and data management and connectivity management for each mobility softwares and IoT devices. So by using this data platform, every ARM-based chip and devices is connected to this Perion platform, and Treasure Data is the core system to collect these data from the IoT devices in near future. So this is our Treasure Data. So now this is a main part of this talk. I'm going to describe what kind of challenges we have for now and what kind of approach we take to solve these problems. So first, what is distributed data analysis? In definition, distributed data analysis is the system or application to process large-scale data which cannot be processed by only single node machine or single disk or small amount of memory, CPUs. So by using multiple node instances, we can distribute the large-scale workload into the small part of segments. And also, by distributing workload into multiple worker instances, we can achieve high throughput by distributed data analysis. And in addition, high availability and reliability can be achieved by using distributed analysis because modern softwares for distributed data analysis is designed to keep running even if one or two node instances is down. So by using this kind of software or architecture, we can achieve high availability and reliability. And last but not least, data consistency is very important. When we want to update the data or delete the data, we don't want that kind of data is visible to our users. So we, as like the traditional RDBMS system, these distributed data analysis system need to keep data consistency always. So that is distributed data analysis we are talking about. And as most of you know always, distributed processing engines is published as open source softwares. The famous one is Hadoop. This is the more than 10 years old softwares, and many applications can run on that softwares. Of course, we are using Hadoop too. And Presto is another SQL processing engine. It's very similar to Hive, but Presto is an on-memory processing engine. So it does not use disk, but the speed is much higher than the Hive, so it can be used for interactive query analysis or ad hoc analysis. And as well as the Presto, Spark is also the on-memory processing engine, but Presto only has a SQL interface, but Spark has several kind of interfaces like SQL or streaming engine processing, machine learning, and graph engine execution engine. And this is the typical architecture of this kind of distributed data analysis platform. They are based on the master worker model. So one cluster has one master node and multiple worker nodes. So first, we want to do some workload to these clusters. The client needs to send a request to master node, in this case, coordinator. And master node, after the master node gets the request from the client, it passes the request and create a logical plan and analyze the query itself. And based on the statistics of the underlying storage layer, it can create a physical distributed execution plan. And after that, it passes the plan to the scheduler in the master node, and the scheduler decides which task fragment will be assigned to each worker node. And after scheduled, each task is scheduled, worker node receives the task segment and get it processed and return the result to the client. So this is the basic model of the master worker model. Hadoop and Presto and Spark, all these three softwares uses this kind of architecture. So this is the architecture you should know before deeper dive into the following sections. And this is the picture of how distributed plan looks like. When you submit a query like left picture into the Presto, it will convert it into the right picture. This is the Presto physical execution plan. So in the left query, it just select the class and feature column and aggregate it by each record, and it's joining the table 1 and table 2 by partitioning key class. So in the right picture, it will convert the execution plan like in the right picture, and this execution plan can be parallelized into multiple worker node, so that it only one plan, one task segment can process only small amount of data, so that it can be can achieve the more high performance and more resiliency. So, but even if we use such kind of state-of-the-art distributed analysis platform, we still have many challenges. The first is network bandwidth. Even if we distributed each task segment into multiple worker node, getting the data from the underlying storage is can be a bottleneck because of the network bandwidth. So we want to reduce that kind of bandwidth as much as possible. And also, transactional processing is the key to achieve the data consistency. Without ensuring the transactional processing, some data can be missing and some data can be added even if we want to do. So transactional processing is key to ensure the data consistency in our platform. And system reliability is also the important point. Otherwise, people cannot keep using our platform. So this is the main part of this topic. Here is our approach. First, we are using Columnar Storage, MessagePack based columnar format, and thanks to that format, we can achieve the low network bandwidth. And also, in order to achieve further low network bandwidth, we use the time index pushdown architecture I'm going to describe later. And the last but not least, this partitioning layout is needed to, we found these partitioning layouts should be keep optimizing through a long term. So we created mechanisms to repartitioning or optimizing partition layout continuously. So first, columnar storage. So columnar storage is a general design for OLAP workload, online analysis processing. In the most famous data platform or softwares already uses columnar storage format. The main advantage of using columnar storage format is the saving I/O bandwidth, because it does not need all columns from the underlying storage always. It only needs to pick up some columns which is necessary to the client. So we can omit reading the unnecessary column records. And also, another good advantage of using columnar storage format is compression. By consolidating all similar column values into one section, we can apply the more efficient compression algorithms in the columnar storage format. Because if we know all values in the column, all values in the format is integer type, we can use the run length encoding or dictionary encoding. So that's the key, or that's another good advantage of using columnar storage format. And as most of you know, the famous columnar storage format is Parquet or ORC. They are published as open source softwares, but we take the another columnar storage format. We created another columnar storage format based on MessagePack. MessagePack is a JSON-like binary serialization format that is created by our co-founder, who has Sadayuki originally. So we are using MessagePack from the birth of treasure data. MessagePack is faster, and MessagePack is basically compatible with JSON-like values, but it's much faster and smaller. And we already have over 100 implementations to encode MessagePack values, so we can use MessagePack from any language or frameworks. Based on the MessagePack, we are creating new columnar storage format. The big advantage of using MessagePack in columnar storage format is type system. As MessagePack already has its own type system in the format, so without knowing the actual type, we only need to read the MessagePack file, and then we can know each value is which type. So MessagePack is a type embedded file format. The good thing of this point is we can achieve schema on read in the database system, because underlying storage is already have a type system in the file format itself. We don't need to specify the schema in the other place, because all we need to know the type schema is just read the file itself, because the type is already embedded in the file format. So the good thing of this thing is users can import their data immediately if they want. They don't need to specify the table schema before they import the data. They just import the data in a MessagePack format. And already that file format already has the type system. And by using this MessagePack-based columnar format as a columnar storage format, we can reduce the network bandwidth and storage space efficiently. So in addition to the saving network bandwidth, we can obtain the schema on read feature in our storage system. So that's the reason why we use MessagePack-based columnar format instead of Parquet or ORC. This is a diagram of how schema on read works. So in the underlying layer, we have a MessagePack file data. Here, it's described as a JSON-like format, but it's in the MessagePack. And when we want to read that data, we already know the type of each values. So if we want to read this MessagePack into the Hive or Presto, all we need to do is mapping MessagePack type into the Presto type or Hive type. So our user does not need to specify the schema of this table explicitly. They all they need to do is just importing the data in our storage in MessagePack format and read the data by using our Presto or Hive. And another approach to reduce the I/O bandwidth is time index pushdown. So time index pushdown is very simple approach, read skipping by time range. That's all. So this is found by the analysis of our users' use cases, because in our OLAP analytical use cases, people use filtered out by time range, which means, for example, they want to create their report by month or by week or yesterday's report. So in that case, they don't need the records in the other time ranges. So if we want to create the report in the last month, they don't need to correct the record in this month or older months. So just filtering the record by time range can reduce the network bandwidth further. And in order to achieve time index pushdown, we use PostgreSQL. In this PostgreSQL, it stores the time ranges of each partition files in the record. And by using PostgreSQL, we can achieve the transactional update. So if we want to delete one partition or update one partition, they can be updated by using PostgreSQL transaction itself. So the PostgreSQL index can work as a kind of snapshot of our storage system, so that we can provide a kind of sort of snapshot isolation in this PostgreSQL-based storage system. And the second reason of using the PostgreSQL is PostgreSQL provides a GIST index, so that we can achieve the create multi-column index efficiently, because we need to create index on the table ID and time ranges. So we need to create multi-column index efficiently. So GIST index enables us to do that. So this is the diagram of how time range partitioning and time range index is working. So in the left picture, this side picture shows the record in the PostgreSQL, and it stores the actual file path and the time ranges each partition file record has. So in the left top record, it stores the data in the 2015 December 1st to 2015 December 1st, 11 o'clock. And the second record stores the data from the 11 o'clock to 12 o'clock. So by first Presto and Hive system in our platform, check the index in this PostgreSQL and select the only necessary metadata by specifying the type ranges. So if we want to get only the records in the time range from 11 o'clock to 12 o'clock, our Presto only needs to get that information. And after that, we need to download the actual data file from the underlying storage system like S3, but Presto only needs to access one file. So in the write down file, because it only has the record from 11 o'clock to 12 o'clock. We don't need to access the above files. So that can reduce the amount of network I/O bandwidth. And this is a picture of how time index pushdown work. So as you can see, just by reducing the time range narrower, we can achieve more faster query. So it shows the by specifying the time ranges in more strictly, we can achieve the more good performance. So that's the final challenge. But how can we decide the partition sizes? So initially, we use this metrics, this configuration for the partition files. 1 million records per file or 256 megabytes per file. That's based on our experience. But recently we found the best partition file size is highly dependent on the actual customer workload. So we need to create repartitioning the underlying storage layer continuously based on the client use cases or workload. So they need to resize the partition size. We need to change the time ranges of each partition files, and we need to change the partitioning key instead of using time range. So because the reason why we need to keep searching the best partition file is this. So small distributed partition files can cause a high I/O overhead because Presto system or Hive system needs a lot of small partition files. So that can cause a high I/O overhead. And also in the Presto or Hive system, they need to keep each partition metadata. So it also has a high memory pressure on the master node. So we need to keep partition file. We should not make each partition file small. But large partition files can cause another problem, because we need to, in the Presto system, we need to load the partition file into memory. So if the one partition file is very large, it can also have a memory pressure. So we need to seek the good balance of the partition files. And also, as I mentioned before, we need to keep searching the good partitioning key, because in the initial experiment, our customer uses the time range filtering. They want to create a report in the week or in the last month, but recently their workload can be changed gradually. Some customers uses some customer creates a segmentation by user ID or purchase item. So they need to scan full partition files, but only some amount of user ID record or purchase item record. So in that case, time index pushdown does not work. We need to create another way to filter out by using another partitioning key, not time index key. So that's we created one, user-defined partitioning key. User-defined partitioning is a partitioning strategy. Our customer can specify any kind of key in the table. So instead of using the default partition key time, they can use their own customer key. So in the left side is the traditional time index key partitioning files. So that is 1 hour partitioning. Each block express the one partition file. And by specifying column 1, C1, column 1 is equal to V1, and time is blah, blah, blah. So the pink block is read by the system. Unfortunately, these pink blocks includes the unnecessary records, which means C1 is equal to V2 or V3. We only need to read V1 records. So by using the user-defined partitioning key, we can omit to read unnecessary records like demonstrated in the right picture. So by specifying C1 is equal to V1, our user-defined partitioning strategy exactly reads the records including the V1 column. So we can reduce the reading of unnecessary records in this case. So that's the big advantage of using user-defined partitioning. And this is a comparison between normal time index pushdown and user-defined partitioning. The left one is count one filter. It's just filtering by some user-defined partitioning key. The performance is much better. But the interesting thing about the group by and hash join pattern, they does not filter out by the user-defined partitioning key, but the performance is much better. The reason why group by or hash join is much better is here. They can be leveraged by the collocated join. So in the user-defined partitioning key pattern, the worker node, table scan node can correct the specific key records in advance. So in the normal case, in distributed join normal case, they need to shuffle all records to the upstream worker node. So they need to consume a lot of network bandwidth to correct the same key record in one node. But in the case when collocated join is enabled, like user-defined partitioning key, all table scan node already have a same key record in one node. So they don't need to reshuffle the record to correct the same key values in one worker node. So that's the reason why we can achieve high performance even in group by or hash join. But some cases, user-defined partitioning does not work because the granularity of each partitioning is smaller by using user partitioning. So reading, as I said before, reading small partitioning files can be overhead. So we need to still be careful to use user-defined partitioning in some cases. So in order to keep this storage layout, user-defined partitioning, we created another breast connector, which is called Stella Connector. And by using this Stella Connector, we can keep the most efficient storage layout continuously. The reason why we use Presto as this repartitioning system is high scalability and reliability of Presto. So reading a lot of partition files and repartitioning of these files is very high workload. So creating another system to do so is take much cost. So instead of creating another system, we need to use the Presto system because it always achieves high scalability and reliability. This is a diagram of Stella Connector. We can submit a Stella SQL to represent the repartitioning job. As this SQL shows, we can specify max file size and max time range in this query. And Stella Connector reads all partitions in the Presto cluster and distributed task segment to each worker. Each worker reads the target time ranges or target key values records and remerge the into the big partition files and rewrite the underlying storage layer. By using Stella Connector, we can keep the best partitioning layout in our storage layer. And Stella Connector is scalable and reliable because it's using the Presto. And by using Presto, we can easily integrate it into workflow engine because that's the SQL, that's the just SQL job. So as I described before, we can use DigDag to schedule each optimizing staging layout jobs into our workflow engine DigDag. So that's the reason why we call it automatic storage optimizations. DigDag can continuously keep running and keep optimizing our storage layout. So basically, that's it. So I introduced some overview about treasure data and architecture of distributed data analysis. And I introduced some approaches to solve these challenges we have based on our experience. Yeah, thank you. Any questions? Yeah.
Одну секунду, я вам дам микрофон.
Greetings. Thanks for the speech. Could you tell me, do you use LLVM in some way in your distributed MPP?
Actually, not in our distributed system like Presto and Hadoop. They are all written in basically Java or Scala. So we don't have a place to use LLVM for now.
I see. And another question, what kind of statistics do you use to optimize join order? Do you use it at all?
Join order means, you mean?
Order over tables to join.
Yeah,
there are
yeah.
3 tables and you can join it.
Actually, Presto query engine does not support the join reordering for now. I think the latest ones already supports, but our Presto is a little bit older, so that we did not use the join reordering optimization for now.
So Presto handles it for you?
In near future. So by implementing our connector to provide statistics like the number of records in the partition files, our Presto will handle the join reordering optimizations instead of by ourselves. Because in the latest Presto has a cost-based optimizer, so that cost-based optimizer can handle the join reordering optimization.
Yeah, it can measure how good is the cost of the plan. Okay, I see. Thank you.
Thank you.
Еще вопросы?
Hi, thank you for your talk. Do you store different columns in different files or it all in one file physically on S3?
Actually, not in one file has some specific column.
So
not
you
all.
store some columns on different files and
Yeah.
some columns all together?
Yeah. It's based on the size of each partition files or number of records.
So you can repartition this
Yeah,
too?
right.
Okay, thank you.
Hi. Sorry, how are you doing repartitioning with S3? You cannot just update one location, or how you're rewriting files? And second question, Stella Connector, is it open sourced or it's a commercial solution?
Okay, so the first question is how to update each partition in the S3, right? Yes. Okay, so as I explained in the middle of this presentation, the metadata, all metadata is stored in the PostgreSQL, and it includes the actual S3 path in each record. So we don't rewrite each partition in the actual S3 file. We only just need to update the path in the PostgreSQL metadata, and it can be updated by using transaction atomically. So by just updating the metadata side, we can replace the partitions in the underlying storage. Does it make sense?
But do you use Parquet files for storing data or message? It was like MessagePack and columnar format. It's like some special column format, or you don't support like Parquet format or C?
Yeah. For now, we don't support other file format. Only support MessagePack-based columnar format. Not ORC or Parquet.
And how many records you have in each file?
Basically about 1 million records per
1 million
partition
records.
file.
Okay, thank you very much. And what
the-
about Stella Connector? Is it open source?
It's not open source yet, and we have not planned to publish that.
The previous guy asked you about how do you repartition the files, but you also mentioned that you have files that contains more than one column's data. So how do you repartition if you, for example, need to segregate one column from the number of columns that are in one file?
So all metadata is stored in the PostgreSQL. So by specifying the table ID and time range, we can get all the partition files paths. So our Presto system can collect all necessary partitions, even if they are split into multiple partition files or column blocks.
Yeah, it makes sense. Thanks.